Hello and welcome to today's lesson looking at wave speed, which is found in the GCSE topic of waves. So in today's lesson we're going to try and understand how to calculate wave speed. So if we're successful and we learn in today's lesson, we should be able to describe the process of wave speed, understand that waves have a finite speed and the consequences this has for the universe, and then finally calculate the wave speed for a wave. Now in today's lesson we're looking at the following part of the AQA GCSE separate science specification for physics. So we're looking at 4.6.1.2 properties of waves, and we're going to be looking at the wave speed equation in today's lesson, which is suitable once again for students carrying out AQA GCSE separate science, and we're looking at the waves topic, which is topic 6 of the GCSE specification. So what do we know? Well, a wave is a periodic disturbance in a material or space. Now, each particle of a medium vibrates or oscillates about a fixed position, and this vibration allows energy to be transferred in the universe. Now, waves that move outwards from the source we call progressive or traveling waves, and we can actually have two separate characters for progressive waves: transverse waves and longitudinal waves. Now, a transverse wave is when the wave oscillates perpendicular to the direction of energy transfer, or sometimes we call propagation of the wave. So a transverse wave can be modelled by moving one end of a slinky up and down. Each coil of the slinky represents a particle. So as the source moves up and down, the coil vibrates up and down, but the direction of energy transfer, the direction of propagation, is actually going across that particular motion. So it's oscillating perpendicular to the direction of energy transfer. Now in longitudinal waves, the wave oscillates parallel to the direction of energy transfer or propagation. So longitudinal waves can also be modelled by moving one end of a slinky back and forth, and each coil representing a particle. So in this particular example, as the source moves left to right, the coil vibrates left to right, but the direction of energy transfer is in the same direction as the coils that are vibrating. Now, within longitudinal waves, regions in which the particles are relatively close together, there's a high density, are called compressions, and the regions where the particles are relatively far apart, there's a low density, are called rarefactions. So as a result, you've got compression, rarefaction, compression, rarefraction. So in compressions, the particles are very close together, so we can say that there's a high density, whilst in a rarefaction, the particles are more spread out. So the rarefraction, there is a low density of the wave. Now, these effects are observed in mechanical waves, as these waves are vibrations of particles. So we can observe it here in this animation. You can see in this animation of a longitudinal wave that our particles are oscillating about fixed positions, and you get a compression, rarefraction, traveling through the wave. Now we can also look at this in terms of sound wave, which is an example of a longitudinal wave. Now remember, if there was no particles in this particular example, there will be no wave, because the sound wave is a mechanical wave. So we've got our compressions where the particles are close together. There is a high density of air, whilst the rarefactions are the areas in the air which are of a low density, the particles are far apart. So we can actually look at a comparison between the two types of waves with the following. So an example of a longitudinal wave is a sound wave. So you get compression, rarefraction, as the wave oscillates parallel to the direction of energy transfer. But in the transverse wave, the wave has oscillations perpendicular to that of the energy transfer, such as in a water or ocean wave. So whilst the wave vibrates in one direction, the energy is transferred in a direction 90 degrees to that. So we can also further classify waves as either mechanical or electromagnetic waves. Mechanical waves are oscillations of particles in a physical medium. This can't transfer energy in a vacuum, because in a vacuum there are no particles, and mechanical waves can be either transverse or longitudinal. So examples of mechanical waves include sound waves, seismic waves, and water waves. But electromagnetic waves, sometimes shortened to EM, are oscillations of the electromagnetic field lines, which is found everywhere in the universe. So unlike mechanical waves, they can transmit energy through a vacuum, but they always have to be transverse waves. Now, examples of electromagnetic waves include microwaves, X-rays, visible light, infrared radiation. Now, all waves are oscillations and transfer energy without the net movement of matter. This means that a sound wave can transfer energy to your eardrum from a far speaker without the air particles moving towards your ear. So they will oscillate backwards and forwards, so they won't have a net change in position. So we say the overall particle displacement is zero. Therefore, the particles do not move on average. Now remember that even though the particles are oscillating, the average position of the particle never changes, which is why producing the sound does not create a vacuum in the air as it travels through. So you've got to remember that idea. So let's just clarify what we've learned so far. A longitudinal wave is when the oscillations are parallel to the direction of propagation, energy transfer. When the particles are close together, we call that a compression, and when they're spread out, we call that a rarefaction. The wavelength is the distance from one compression or refraction to the next corresponding value in the next wave, and the amplitude is the maximum distance a particle moves from equilibrium to the right or the left. Now, in a transverse wave, the oscillations are perpendicular to the direction of energy transfer. When the particles are displaced above the equilibrium, we call that position a peak. Below it, we call it a trough. The wavelength is the distance from one peak or trough to the corresponding peak or trough in the next wave, and the amplitude is the maximum displacement the particle moves from the equilibrium position either up or down. Now, we can work out how fast a wave travels in a medium by carrying out the following calculation. Wave speed in meters per second is equal to frequency in hertz times by the wavelength in meters. Now, you will have to recall and apply this equation for your examination, and this equation shows how fast a wave transfers energy throughout the universe. So the speed of a wave is the distance travelled by each wave every second through a particular medium. Now, all waves have a finite speed, so it takes time for energy to propagate from one place to another place in the universe. Now, in many ways, such as light waves, this time is not perceivable to human senses, so it feels instantaneous, but that time is still present. Every energy transfer is never instantaneous. This equation cannot be used to work out anything but the speed of a wave. Now, for this equation to work correctly, you've got to have your frequency of your wave in hertz and your wavelength in meters. This may mean you've got to convert the units of the values given in questions. Now, this equation makes sense when you consider what the terms of frequency and wavelength are, because we know that frequency is the number of waves per second and the wavelength is the length of one wave. So if you multiply the two values together, you're getting the distance travelled by the wave in 1 second, which is what the wave speed of a wave is. Another way you can think about it is think about the equations that work out these values. So frequency is 1 over time period, wavelength is equal to distance, so wave speed is therefore 1 over time period times by distance. So therefore wave speed is going to be equal to distance divided by time. And what do we know? Well, that's the same equation for speed is covered in the forces topic. Speed equals distance over time. So it's actually just another way to write out that particular equation. Now, the speed of all electromagnetic waves in the universe in a vacuum is 3.0 times 10 to the 8 meters per second. That's the fastest possible speed in the universe. Nothing can travel faster, and electromagnetic waves will alter their frequencies and their wavelengths to give a speed of 3.0 times 10 to the 8 meters per second. What that means is the higher the wavelength of an electromagnetic wave, the lower the frequency, and vice versa. The higher the frequency of an electromagnetic wave, the lower the wavelength, because when those two values multiply, it's got to equal 3.0 times 10 to the 8. Now, so we'll just mention that the shorter the wavelength, the higher the frequency. Now, mechanical waves do not have to travel at 3.0 times 10 to the 8 meters per second. They all travel at different speeds. Now, because mechanical waves are the movement of particles, this means the energy actually travels a lot slower than that of electromagnetic waves. If you remember, the speed of a sound wave is 330 meters per second, which is a lot slower than 3.0 times 10 to the 8 meters per second. second. Now, the mechanical wave speed depends on the mass of the particles moving and the density of the materials. Generally, mechanical waves travel faster in solids than in fluids, liquids and gases. That's because the particles are closer together in the solid, the material is denser, so vibrations are more likely to result in an energy transfer because the particles are closer together, so are more likely to knock into each other. Now, just to clarify this concept of hertz. Hertz is simply the number of complete waves per second. It's the unit of frequency. So, for example, 20 hertz means 20 waves per second, either 20 waves created per second by the source or 20 waves passing through a particular point. Now, let's just recap what we have learnt. Electromagnetic waves all travel at the same speed. That's the fastest possible speed in the universe, since electromagnetic waves are massless. The speed of all electromagnetic waves in a vacuum is 3.0 times 10 to the 8 meters per second. Mechanical waves all travel at different speeds, since this depends on the particle mass and density, and mechanical waves contain particles with mass, so travel a lot slower than electromagnetic waves. Now let's look at an example question you could be asked in an examination. So you could be told the wavelength of a wave is 45 meters. The frequency of the same wave is 20 hertz. What's the wave speed of the wave? So you always answer these types of questions in 3 steps. Step 1, write out the equation. To show the examiner you know which equation you're using. Step 2, substitute in the values. This shows the examiner you can recognize the frequency and you can recognize the wavelength. So you do 20 times by 45. You then do step 3, you calculate your answer, and then the answer is 900 meters per second. And always check you give a unit with your answer, meters per second, that's the correct unit, and we've got the correct number of significant figures, so we'll give it to 2 significant figures because that's what's been given in the question. Now, another more challenging question might include prefixes. So in this question, the wavelength of the wave is 24 millimeters, the frequency of the same wave is 31 kilohertz, so what's the wave speed of the wave? So once again, you follow the same procedure. Step 1, write out the equation. Wave speed equals frequency times by wavelength. You substitute in the values, but you've got to convert your prefixes. So kilo means 10 to the 3, so 31 kilohertz becomes 31 times 10 to the 3 hertz. Milli means 10 to the minus 3, so 24 millimeters becomes 24 times 10 to the minus 3 meters. You then calculate your answer and you get 744. But you've got to firstly put your unit on your answer, meters per second, and secondly, give it to the correct number of significant figures. Now there's 2 significant figures in the question, so give your answer to 2 significant figures, so 744 becomes 740 meters per second. Now, if we have learnt in today's lesson, we should be able to remember the following ideas. Wave speed is equal to frequency times by wavelength, where wave speed is in meters per second, frequency is in hertz, and wavelength is in meters, and you should be able to remember that equation and then apply to different situations. So if we're being successful and learnt in today's lesson, we can describe the processes of wave speed, we understand what waves have a finite speed and what that consequence is for the universe, and calculate the wave speed for a wave. I hope you've enjoyed this lesson looking at calculating the wave speed of any wave in the universe, and have a lovely day.